So far in electronic system design, we've looked at some of the problems with using operational amplifiers. We've looked at the errors introduced by offset voltage or offset current or bias current and how this affects your circuits. In this lecture and the following ones, we're going to look at the effect of noise and how that will affect your circuit and how to design low noise amplifiers and circuits that can process low-level signals successfully and effectively. First thing I want to do is talk about the definition of noise. Many people mistake interference with noise. Interference is any unwanted signal which couples into your system. It could be mains hum. It could be switching noise from perhaps large motors or relays or logic switching. It could be RF interference from powerful transmitters or cell phones that are nearby your circuit. These are all interfering things. And finally, it could be crosstalk from stereo channel separation. In other words, the left channel bleeds through into the right channel, or crosstalk from multiplex telephones where you actually pick up somebody else's conversation accidentally on the phone system. You can deal with interference by using improved screening around your circuits, better ground design, isolating your circuits from each other, such as analog and digital grounds in applications, using instrumentation amplifiers, or physically separating the two units. A mobile phone's not going to interfere with your circuit if you put it on the other side of the room. The other challenge with interference is it's very difficult to predict because it's actually a reflection of shortcomings or failings in your circuit design. And here are some interference sources that I'm sure you're going to recognize. The first one is the interference caused by mobile telephones. And now let's hear some other interference that you may pick up. The second one, it would be radio pickup from a powerful transmitter. And the third one is mains-borne interference, or hum loops. And this is the bane of most of audio designers when they're trying to hook up large audio systems. Let's compare interference with noise. Whereas interference is very difficult to predict and manage, noise is fundamentally due to random processes within the components and within the system. Noise can be predicted precisely and can be designed for with high accuracy. Noise is not like interference. It's not just random junk around the circuit. It is actually physical phenomenon that we can predict and manage. What I want to introduce to you now is a concept called signal-to-noise ratio. And this is precisely as it explains. It's a level of signal compared with a level of noise in a particular signal. And this is a particularly problem for sensors because if you have noise in a sensor that is larger than the signal you're looking for, you cannot use the sensor for that application. And within signal processing, whether it be mobile phone, telephony signal processing at RF or audio signal processing for doing effects in music industry, signal-to-noise ratio is critical for that. And signal-to-noise ratio is probably the most critical for communication challenges. Whenever you are dealing with communication problems, noise is always one of the challenges which degrades the quality of the channel that you're trying to communicate over. So you can understand what signal-to-noise ratio sounds like, what I've done here is I've recorded a couple of samples. I've recorded white noise plus a 1 kilohertz tone, the signal, at the same level. And this is defined as a signal-to-noise ratio of 1 or 0 dB. Let's have a listen. The first noise you will hear is white noise. The next sound you will hear is a 1 kHz tone mixed with the white noise. The level of the tone is exactly the same RMS value as the level of the noise. Of course, signal to noise ratios are critical for other applications, and in particular, here's a space application. This is the Deep Space Network, which is responsible for communicating with the moonshots and also the International Space Station. And here they have to use very large antenna in order to keep the noise level received from space down. These antennae are huge, and this is an example of a man standing at the center of the antenna, and you can just see how large it is. And the important thing to realize here, that if you have an amplifier connected to that antenna with 3 dB of noise, your 70-meter antenna has now had to increase to 100 meters just to recover the noise of your amplifier. So good amplifier design is critical to noise performance. Noise can arise from several different sources, and we're going to look at one in particular, but we'll mention some of the others so you can identify them later in your professional life. First one is thermal noise, and that's the one we're going to look at in more detail today. It's like Brownian motion, and it's due to the motion of electrons. It's also called Johnson noise. There's a concept called shot noise. This is due to random emissions of electrons over a barrier, be it a p-n junction, a tunnel diode, or even a thermionic valve. A good example of that is a photodiode, where as photons impinge on the junction, they release electrons, and that gives rise to effectively shot noise. Another concept is flicker noise, sometimes called 1/f noise because it has a reducing effect at higher frequency. And it's due to the random capture and emission of charges inside a device. In reality, it's actually a reflection of how well and how good your processing of electronic devices actually is during manufacture. And the final one is popcorn noise. And these are bursts of a current in active devices, sort of like flicker noise, but the individual events are not fully resolved, and you land up with changes in the level of the noise that's coming out of your circuit. Thermal noise always exists in any environment unless it's less than absolute zero. But shot, flicker and popcorn noise require current to be flowing in the circuit before it will actually occur. And some of these, they have to be active devices, junctions in place before the noise gives rise to a problem. And here is 3 examples of the noise. In popcorn noise, you can see that it's actually very large level signals that jump up and down between 2 levels, and they sound just like popcorn bursting in a pan. The flicker noise, we have frequency along the bottom here, and we have a 1/f relationship here. It would actually keep going down to 0, but it then gets overcome by the thermal noise. And the last one is thermal noise, quite often called white noise, and that's the third one we're going to look at. Those are the key points of noise, and the next lecture we're going to look at how you manage and calculate out some of these figures in order to improve your circuits. Thank you.